Hi friends, today we see about finite element method one-dimensional problems. We have discussed such things in the previous session, previous videos. So now we have to see material type. What are the beam as well as bore? What kind of material to be used? And upon the material, it has some characteristics during the deformation, depend upon the application of loads. Homogeneous material. A beam element has the same material composition throughout and therefore the same mechanical property at every position in a material. Therefore, modulus of elasticity is constant throughout the beam element. A member in which the material properties varies from one point to next in the member is called inhomogeneous. If a beam is composed of different types of material, then it must be divided up into elements and or each of a single homogeneous material. Otherwise, the solution will not be exact. Isotropic material. A beam element has the same mechanical and physical properties in all directions. That is, they are independent of direction. For instance, cutting out three tensile test specimen, one in x direction, one in y direction, and the other oriented 45 degree in xy plane. The tension test each specimen will result in the same value for the modulus of elasticity. Yield strength and ultimate strength, most metal are considered isotropic. In contrast, fibrous materials such as wood typically have properties that are directly dependent and are generally considered anisotropic, not isotropic. Rigid body motion occurs when force and or momentum are applied to an unrestrained mesh, that is body, resulting in motion that occurs without any deformation in the entire mesh, that is body. Since no strain deformation occur during rigid body motion, there can be stresses developed in the mesh in order to obtain uniform solution. A rigid body motion must be considered. If rigid body motion is not considered, then the singular system of equation will result, since the determinant of mesh stiffness matrix is equal to 0. There are two rigid body modes for one-dimensional beam elements, a translation, that is displacements manually and rotations manually. These two rigid body modes can occur at the same time, resulting in a displacement and a rotation simultaneously. In order to eliminate rigid body motion in one-dimensional beam element, this body, one must prescribe at least two nodal degrees of freedom, either two displacements or displacement and a rotation. A degrees of freedom can be equal to 0 or a non-zero known as n value. As long as the element is restrained from rigid body motion, deformation can take place when forces and moments are applied. For simplicity, we will introduce the rigid body modes using a mesh composed of single element. If only translational rigid body motion occurs, then the displacement at local node will be equal to the displacement local node j. Since the displacements are equal, there is no strain developed in the element and the applied nodal forces cause the element to move in a rigid, that is non-deflected vertical motion, which can be either up or shown below, or it can be in the downward direction depending on the direction of the applied force. This is the derivation of shape function and stiffness matrix for one-dimensional Bohr element. Consider a Bohr element with nodes 1 and 2 are shown with the displacements of u1 and u2 at the respective nodes. The displacement u can be given as u is equal to a0 plus a1x. a0 and a1 is general coordinates. U is equal to 1x, then a0 a1 vector at node 1 u is equal to u1, x is equal to 0. At node 2, u is equal to u2 and x is equal to L. Substituting in my equation 1, we convert into matrix form u1, u2 and 1, 0, 1, L, then a0, a1 vector. So a0, a1 vector is equal to matrix 1, 0, 1, L inverse. So then displacement vector u1, u2, a0, a1 is equal to 1 by L, 1, 0, minus 1, 1. So u1, u2, substituting in equation 2, so u is equal to 1 x, 1 by L, 1, 0, minus 1, 1. So displacement vector u1, u2, finally u is equal to L minus x by L, then x by L. So displacement u is equal to n1, n2, then u1, u2 displacement vectors. So n1 is equal to Lx minus x by L and n2 is equal to x by L. n1 and n2 are shape functions. The stiffness matrix K is equal to integral B transpose T, then D matrix, then B into dV, where B is the strain displacement relationship matrix, D elasticity matrix. So B matrix is equal to dn1 by dx, dn2 by dx is equal to minus 1 by L, 1 by L, and B transpose equal to minus 1 by L, 1 by L. One dimensional problems, it is D is equal to Young's modulus dV is equal to A into dx. So we get the stiffness matrix equal to AE by L, 1 minus 1 minus 1 1 is the stiffness matrix for one dimensional Bohr element. So next to that, what is the type of loading we could be used? That is first one, body force, that is F, distributed force per unit volume. Example, self weight due to gravity. Then traction force, force per unit area. That is frictional forces, viscous drag and surface shear. Then point load, concentrated at a point. Steps in finite element modeling of a one-dimensional Bohr element. The first step is to subdivide the Bohr called discretization. A non-uniform Bohr is transformed into uniform taper Bohr. Second one, numbering of nodes. Third one, natural coordinates. Consider a single element. Local node 1 is at the distance of x1 from the datum and node 2 is x2 measured from the same datum point. Shape functions. Establish a linear interpolation function to represent linear displacement field within the element. Linear shape functions are given by, so n epsilon is equal to 1 minus epsilon by 2 and n2 is equal to 1 plus epsilon by 2. Example, a thin steel plate of uniform thickness 25 mm is subjected to point load of 420 Newton at mid depth as shown. The plate is also self-weight. If Young's modulus E is equal to 2 into 10 power 5 Newton per mm square and the weight density 0.8 into 10 power 4 Newton per mm cube, calculate displacement at each nodal point, stress and each element. This is a diagram shown. So we can split up into two elements. So here we are using the formula F1 F2 is equal to rho 1 A1 L1 divided by 2 into vector 1 1. So from which we can calculate the value force F1 F2 F3 is equal to 20 36 then 60. The point load of 420 added at the midpoint so far. So 420 plus 36 is equal to 456 in the middle of that value. Finite element equations for first element 2500 into 2 into 10 power 5 200 1 minus 1 minus 1 1 u1 u2 is equal to, that is the force vector for first element. Likewise we can calculate the second element. It's the combination of 3. So f1 f2 f3 is equal to 2 into 10 power 5, 12.5 minus 12.5 0 minus 12.5, 12.5 plus 10 minus 10, 0 minus 10 minus 10, then displacement vectors u1 u2 u3. Apply boundary conditions that node 1 displacement is 0. Substituting the values of force we get, then u2 is equal to 1.888 10 power 4 mm, uy is equal to 1.9688 10 power 4 mm. The stress is equal to E into du by dx, from which we can calculate the value of stress at element 1 is equal to 0.188 Newton per mm square, and sigma 2 is equal to 0.008 Newton per meter square.